First of all, thank you very much for trusting me to come to give you these lectures. I will talk about a body of literature on mechanism design. And I know a lot of you know a lot about mechanism design in economic theory. So this is a special part of mechanism design where the designer is also a strategic player. And there are a number of subtleties that arise in this type of environment that are also transferable in other situations where we're thinking about the designer as being a player in a strategic setting. So the title of this lecture is Limited Commitment, Mechanism Design Meets Information Design. And I will talk about pure theory, but also I will apply the tools and the theory we're going to develop in the first lecture to a problem of designing histories or data sets, if you like, from past purchases, which are what the designer is going to design in the first period interaction, that then the designer, which can be the same designer or another designer, can exploit at a subsequent interaction. So if you think about a vertical relationship, an upstream firm collects data and sells it to a downstream firm. That's going to be our second lecture. This lecture is drawn on work I've been doing since my thesis, but primarily on work I've done recently with extremely talented and gifted theorist, Laura Duval, who is also a very dear friend of mine. So most of the lecture will be based on joint work with Laura. So as I was alluding to a minute ago, the first lecture is going to talk about the background, what is the problem we're looking at, and it's going to give you some perspective of the first seminal papers by Besser and Strauss on the topic. And then we're going to talk about our revelation principle under limited commitment and introduce to you the class of mechanisms that are without loss of generality in those settings, which we call direct Blackwell mechanisms. Direct Blackwell mechanisms are a class of mechanisms that I will show you in a minute and includes the standard direct revelation mechanisms that we use, that we are more familiar with. So it's a class that is encompassing the standard canonical class, if I'm making any sense. And then I'm going to illustrate the theory with a very simple two-period model and show you how we can use this new revelation principle to express the designer's problem, again, as a constraint optimization problem, which is much simpler to analyze than a complicated game with a player who is choosing mechanisms. And the second lecture is going to think about the application of thinking about mechanism design as data set design in a way. So we're going to think about the application will be about how the purchase history and product personalization are shaped in an upstream downstream interaction where the firm uses past purchase history to price discriminate in the second period. And we're going to see some type of how this language we're going to develop in the first lecture is going to help us find what is the optimum product line for the upstream seller and how this design of product affects pricing and welfare and so forth, which are the things we care about in economic settings, right? We want to think about, after we design the institution, what are the implications, what are the new frictions we get, and what are the welfare implications or any regulatory issues that we could address with the framework. Sorry, that was the wrong direction. Okay, so let's start with a kind of broad picture and where we are. So as we all know, I guess a lot of you know a lot about mechanism design, but if something is unclear, please raise your hand and don't be, this is a class, this is not a seminar. This lecture is primarily for you, not for me. So I would really like you to feel comfortable to raise your hand and ask whatever you like. It doesn't have to be, it has to be, any question is a good question. So please ask anything you want. The lecture is for you. So we kind of know, all of us more or less, mechanism design is the part of economics that thinks about designing markets or institutions. And it's sort of I read this quote once in The Economist and I thought it's wonderful. It's mechanism design is the helping hand to the invisible hand. So how we help kind of markets perform better, and it has been successfully applied to many settings, from auctions, regulations, social insurance, taxations, and so forth. So when we're thinking about designing what is the best institution, of course, that is a very complicated problem because we're thinking about what is the set of rules among all set of rules that is the best according to some objective. And this question is even writing down all set of rules is a very complicated thing to do. But we have seen tremendous progress in mechanism design thanks to a fundamental result, which is called the revelation principle. This result underpins the broad applicability of mechanism design. And in particular, in a dynamic setting, this result says, well, take an arbitrary sequence of mechanisms together with the agent strategy and think about now what is the outcomes we are going to get when we think about the agent best responding to the sequence of mechanisms. So the mechanisms can be arbitrary and complicated. The agent strategy can be arbitrary and complicated, but it has to be some optimal response in a strategic setting. The revelation principle says in a dynamic setting that we can replicate the same distribution over outcomes, which is joint distributions over types and ultimate allocations, who gets what, with a sequence of direct revelation mechanisms where the strategy space of the agent is simply to make a report about their type. And it is not just that we get a simple class of mechanisms, we also get simple behavior. In particular, telling the truth and participating using that as the best response with our sequence of direct mechanism is enough to replicate the thing that what arises from an arbitrary sequence of mechanisms. And this makes the problem very well tractable because essentially that what we get, is that because we can basically replace the agent here, which is a strategic player, is essentially captured with the two constraints, telling the truth and participating, and effectively transforms the equilibrium problem into a constraint optimization problem. So instead of solving for equilibrium, we are solving a decision problem, much simpler. So now the problem is that the applicability of the revelation principle relies on the designer's ability to commit to the entire sequence of mechanisms. And this commitment assumption is often unrealistic. So if you think about firms, they accumulate data about consumers over time, and they're tempted to use this data to change the pricing, the terms of contracts. The same, in a similar vein, benevolent governments are long-lived, but they cannot bind the successors. So if I'm a government, I can design a policy for today, but no one promises that this policy is going to be adopted by the future incumbents. So in practice, that's a quote from the Nobel Prize Committee when they were commenting on Jean Tirol's work on regulation. In practice, regulation is seldom once and for all, but rather an activity that takes place over an extended period. The regulator may be unable to commit to a regulatory policy over the relevant time span. So it's not just that, the assumption is unrealistic. The optimal mechanisms we get are hard to swallow. So they are time inconsistent. For example, if we're thinking about the optimal mechanism of for a seller of a durable good, so you are a seller, you have a unit of a durable good, let's say it's, a fringe, something durable, you set the optimal mechanism is to charge a constant price. So you choose a price and then you never change it. But if you choose a price and you don't sell the good, then you are committed to remove the object from the market. The same thing in context of taxation, the same contract has to be repeated every period, but that's not sequentially rational because once the regulator realizes, this firm is actually an efficient firm and can produce at a lower cost, then the regulator wants to demand, more production and less subsidy for the firm. That's where we are. That's sort of we're going to be thinking about now a mechanism designer who has imperfect commitment. So under limited commitment, the designer is now a player. The designer strategically exploits revealed information by the agent. Because the agent expects, well, today there's a mechanism, we know the rules, that's great, but whatever the designer learns about me from this interaction, that could be exploited. The agent is reluctant to reveal private information. And the intuition is that types that reveal either through reporting, but ultimately, through behavior, they lose information rents. And in that sense, the classic revelation principle no longer applies. In particular, it is not just the case that we don't have, truth-telling as a canonical best response. Truth-telling may not even be a best response. So Lafon and Tirol, they have a seminal paper in Econometrica in 1988. Actually, this is a paper in Econometrica that has a problem, but not a full solution. They show that in a two-period regulation problem under limited commitment, a standard sort of two-period, the standard regulation problem, Baron, Besank or Baron-Myerson type of problem, repeated twice, you cannot find the optimum. And actually, they show that in the first period, it might be impossible to separate a continuum of types. So the core conceptual difficulty is the following. The designer's current payoff depends on future choices, future mechanism choices, which depend on posterior beliefs about agent's type. So I'm in period 2. I'm going to choose the mechanism now that I have observed the behavior of the agent. I've updated my beliefs, so now I'm going to choose a second period mechanism. This mechanism depends on my beliefs, but these beliefs about the agent's type are themselves mechanism dependent, because the agent in period 1 thinks about, well, what will my behavior in period 1 do to the principal's belief in period 2, because this will affect the mechanism I will see tomorrow. So this creates this conceptual difficulty that the beliefs are past and future mechanism dependent. And the lack of commit, and then I'm quoting from the book, Lafon and Tirol have a big book on regulation. This was sort of back in the day when I was young. This was sort of a nice book to read when you were interested in regulation, which was sort of the older term for market design, sort of the more the loose term of thinking about, how to fix markets. And this is sort of was considered one of the kind of Bibles of regulation that was written by Lafon and Tirol. And they have several chapters on imperfect commitment, and they write in the book, the lack of commitment in repeated adverse election situations leads to substantial difficulties for contract theory. So, in a sense, the literature a little bit paused at the beginning of the 90s. Yes, please.
Just a clarification question.
Yes.
So you are calling it a limited committed case,
Yes.
not the no committing case. So is that because you are assuming that the mechanism designer can at least commit to the current mechanism?
To the current, yes. And actually, this is an excellent question, because in one slide or 2 slides, I will tell you that although the commitment benchmark is very well defined, lack of commitment can take many shapes, because we can think about designing a contract that is 100 period long, but we are allowed for the possibility of renegotiation. So let's think about, we have 100 period relationship. Commitment says we're going to write a contract that fully specifies everything that's going to happen in the next 100 years. That's commitment. Limited commitment could mean I'm going to write 10 period contracts, or I'm going to write a long contract that I'm going to allow to renegotiate, or I'm going to write period by period contracts. Or I'm going to write, and even in the long-term contract, that could allow for certain levels of memory of the contract. Maybe the contract cannot remember, 80 messages. So all of those things are part of the design. So what we're going to do today this is actually not, I'm not opening a tangent. I'm answering something that I was going to say later, but I think it's important for us to kind of think about this. What we're going to be thinking today, as I'm going to talk about more specifically in a minute, is I'm writing a mechanism for today, but I'm not specifying anything contractually from tomorrow onwards. And this is what some people call no commitment. Some people call limited commitment. I'm going to call it, in the chapter, that I was kindly asked to, I call it kind of spot commitment. So in that's the thing. But in all of those situations that I'm describing, so for example, this is the notion of commitment used in Lafon and Tirol. And this is the notion of commitment, of limited commitment used in the classic papers. That's what I mean with commitment. And this is the notion of limited commitment. I'm sorry. All right. Are we good?
Yeah, thank you.
Okay. So this was actually a good question because I'm going to comment on this, but I should have done it a bit earlier. So thank you for asking this question. All right, so with that in mind, let me just go back 1 second. So with that in mind, think about what I will be saying in the next couple of slides as we commit to the mechanism today, but not to anything tomorrow. Okay, so we have two approaches that have emerged. The one approach, so the literature basically kind of stopped because Lafon and Tirol kind of tried for about a decade, and then it was they stopped. And then there is some work that starts around the late 90s, beginning of 2000. So my paper was published in 2006. I started working on it probably in 1999. You know how it goes with your first chapter for your thesis, how long it takes to get published, at least in my case. So in Best and Strauss, they thought about proving a relation principle. They proved some results that showed, well, if you have finitely many types, you are going to get the truth telling with positive probability. I wanted to solve a problem with a continuum of types where we know truth telling does not hold. Their results were not, actually, I was not aware of their results when I started on my chapter. So when I started working on the problem, I started thinking about it without thinking about the relation principle at all. And what I did, I thought, okay, let's think about this game and think about the implications of the designer's limited commitment and agent's behavior on the set of implementable outcomes, basically on what are the joint distributions of our locations and types we can get at the end of the game. And so let me just I will briefly give you this slide, and then I will stop with the generalities. I know it's frustrating. You are all like highbrow theories. You want to see equations. There's going to be lots of them coming, I promise. But this slide is going to give you sort of the recipe I used. And why am I insisting on some old, approach? Because even though we have a revelation principle today, these problems are inherently hard. So sometimes when you want to solve a problem, relying on different ideas might be useful. And so what I did in my paper, I thought, well, a choice of mechanisms induces a gain for the agent. And as I said, the mechanisms coupled with the agent strategy induce an outcome distribution and the information the designer learns about the agent. So then I asked, if we think about this long game, where the designer is choosing the selling mechanisms, it was a durable good problem I was looking at. What are the implications of the agent strategy being a best response to the mechanisms? And actually, if we think about the implementable outcomes in a buyer-seller relationships, that's basically an expected discounted probability of trade and an expected discounted transfer. So then if you think about these composite objects, you can think of them as every type of the buyer is going to have one of those probabilities and one of those transfers. And an implication of best response is actually truthful. It has to satisfy the self-selectivity constraints. So this self-selectivity that we call truth telling is essentially an implication of best response, but then you could use these composite objects to think about what the sequential rationality tells me about these objects. And that's basically what I did. And with using kind of this sort of like very approach that is not grounded in any canonical language, I was able to give enough structure on what are the PP implementable outcome distributions that I was able to optimize over that and show that the optimal PB implementable outcome arises at simply posted price in every period. Of course, that proof was complicated because I had to show some steps, but in any case, I'm not going to go over that paper. But at this level of generality, you can use this approach without thinking about what is the cardinality of the die space or the nature of the interaction, because it just thinks about the strategic setting and the implications of strategic behavior on outcomes, which are very natural for a game theorist, I think. So the difficulty in the analysis of this problem is something that is a little bit subtle, and it's what one can call it a failure of taxation principle. So in many sort of buyer-seller relationships, or in many firm-consumer relationships, we could think about the mechanism as a direct mechanism. So I report my type theta, and I get a quality Q and a transfer. But we could also think about the buyer choosing out of a menu of qualities and transfers. So I'm just going to offer quality Q1, Q2, Q3, and I'm going to ask the buyer choose one. And of course, the taxation principle says, well, it's with all of the generality asking the buyer to report or asking them to make a choice out of the menu. Are you with me? Now, when you have a dynamic relationship, you could have two different messages or two different strategies leading to the same element in the menu. So it says an orange for like 100 yen. So this item in the menu can be encoding different messages, and the messages could be used by different types. And when I see messages, I not only see the same menu choice, because I get different information that I use differently in the future. And that creates a subtlety. So you could have 10 messages lead to the same allocation, but because these 10 messages are used by different types differentially, they have different posteriors attached to them and different continuations. So this is why this type of approach, although it's useful, can get quite messy quickly. Oh, so now I'm going the wrong way, sorry. Okay, so instead, what we did with our paper with Laura is we developed a revelation principle for mechanism design with limited commitment. And what this result helps us do is to characterize a class of mechanisms and strategies that are enough to implement any outcome distribution that can be implemented under limited commitment. And so now I'm going to Kohiro's question. So we're going to we study a non-informed designer who interacts over time with a privately and persistently informed agent. And the designer offers spot mechanisms, can commit to today's, but not to future mechanisms. So I don't know, can I use this? I don't know how to press the button. So I'm going to give you those slides. So, and I don't want to spend a lot of time talking about, there is a whole taxonomy of, I put some taxonomy here. For example, there is even no commitment to the current mechanism. There is even now some things of committing to smart contracts. We are in this spot. A new 1 period contract is offered in each period, no intertemporal linkages. And if you don't mind, I'll just go back and leave the taxonomy for you to kind of look at later. So what we're going to do in the next steps, we're going to overview the result, the relation principle for this particular class of limited commitment, spot commitment. We didn't write a revelation principle that says what happens when you can commit to 10 periods, 100 periods within negotiation, or where we can think about mechanisms that have memory. We did not do that. And I think one of these prestigious colleagues of yours, like Takuro Yamashita, has a paper working with Nicola Lomis on they thinking about a different form of commitment where there's a long-term mediator and can actually store information and make recommendations to the designer. So this is not what we're going to be thinking about here. Here we're going to be thinking about a current mechanism who doesn't have memory and takes reports today, determines interactions today, and nothing for tomorrow. And within this framework, we're going to introduce a new canonical class, a class that is without loss of generality, which we're going to call direct black hole mechanisms. And then we're going to show how to apply these results. So limited commitment, if you like, is a form of contractual incompleteness because we are contractually specifying what is going to happen today only, but nothing tomorrow. So there are other forms of contractual incompleteness because, for example, we might not have enough language to describe all contingencies. This is not the same here. We're going to have enough language to talk about contractual outcomes today, but we're not going to specify anything about tomorrow. So this type of limited commitment that we're going to be looking at is relevant for the classic settings of regulation, procurement, auctions, and so forth, where we're thinking about one period commitment. Political economy settings, because this one period could be your electoral cycle. It could be 4 years. It doesn't have to be 1 year. So we are thinking about our period as 4 years in situations where we have 4 years elections. And we could also think about this type of limited commitment as a setting where we're thinking about an initial interaction that leaks information. So there are informational externalities. And this is relevant to vertical contracting or aftermarkets, as we're going to explore in the second lecture, and also in privacy design situations where the designer, the upstream designer, who is a firm, let's say Amazon is designing its platform or its pricing policy, it's also functioning as a data broker or selling the data set to another firm. Because this kind of information friction of what is the upstream firm learning from me and how this is going to exploit me is at the heart of this commitment problem here, and also in those types of settings. Okay, so this is sort of a big slide with what we're going to be doing, but we have a lot of time. So I hope maybe it's just too many titles rather than anything else. So let's think about our game. So we're going to, what is actually different from my work and Laura with the works on Western services, where we're fully describing a strategic game, an excessive form game, and then we're going to be thinking about the equilibrium outcomes of that game. So this game has 2 players, a principal and an agent. So notice an important thing we have not done is we have not tackled the case of multiple agents. And that's what I was asked in the one Congress. We worked on it a bit throughout this year, but this is not having multiple agents has other issues that come up that, there are so many new issues that come up with these problems that one can write many papers even to investigate some of the early concerns that arise when you have multiple agents. In particular, the principal might be learning things about players that are non-common knowledge, so you have an informed principal on top of limiting commitment. Because I can be learning things. I'm a principal, I see messages of all of you, but you don't see the messages I'm seeing. So I'm starting to get more information than the agents themselves. Okay, so let's close this parenthesis and let's go back to this. In this game now, there is one principal and one agent. Okay, they are going to interact over some number of periods that could be infinite. The principal holds the bargaining power, so the principal would be designing mechanisms, and the agent has private information persistent for most of the talk, which we're going to index by theta, distribute according to some price. Each period, an allocation A is determined. This allocation can be equality in a transfer, can be a match, for those of you who like matching, can be which candidate won if we're thinking about an election, or which item in the agenda prevailed in current discussions. There is also an allocation A star that represents the agent's outside option. We are going to allow the set of feasible allocations in period T to depend on past allocations in the previous period.
Let's take
Yes.
clarifying question about
Of course.
A star.
Yes.
Once agent get A star, he exits?
No, he can come back
He can come
again.
back.
Of
Okay.
course, yes.
Thank you.
So the getting an outside option does not terminate the relationship.
Okay.
So in particular, if you reject the mechanism and result to A star, then the principal can come back and offer another mechanism. So in a sense, this is also a first step of thinking about negotiating over mechanisms, but the only one party is making the proposal. So the same thing we talk about bargaining, where you have one proposer proposing the split. So here you have one proposer proposing the peace treaty mechanism, for example. So I have the power to propose the trade rules, and the other country says yes or no. But although there's the bargaining power is on one party, the other party has some power because it can say no, 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 no. This is part of this process. So let me come back to what I wanted to say here. So there is a sequence of allocations. And this sequence of allocations can determine what is the set of feasible allocations we can be drawing today. For example, if the past allocations are investment decisions or tasks you did, and there's some learning by doing, what are the feasible things we can get today can depend on all these past choices. Or if we're thinking about addictive behavior. So if we're thinking about the seller selling an addictive good, the level of consumption in the past can affect what they can be offering you today. Of course, it's a terrible example, but it could be learning by doing, but the framework is very general. And also the framework is so general that the payoffs of the designer and the agent depend on the type of the agent, which is persistent. And we have a paper, and we generalize this result to settings where where the agent's type evolves over time. The evolving type is actually simpler in a way, because when I'm learning about theta 1, if the persistence is not very high, the agent doesn't worry about me learning theta 1 because theta 2 is going to be drawn and it's not going to be exactly the same. But if I learn that your type is 100 and I know it forever, that's great because your type is stuck. So then you lose all your information ranks. So that's why in the benchmark paper, we have full persistence. Does it make sense? All right, good. As I said, I'm dumping a lot of information on you, but these lectures are for you, and understanding this, I think, is important, so stop me. So the payoffs depend, at the end of the game, we're going to have a sequence of allocations realized. Obviously, during the game or for the examiner perspective, all of those things are going to be stochastic. But at the end of the game, there's going to be some A of T. From the examiner perspective, there's going to be distribution over those things. But once we have a realized vector of allocations AT, this is the designer's payoff, W, and this is the agent's payoff. Notice that these expressions are not time separable necessarily, and we don't necessarily allow for discounting. So time separability and discounting are special cases. We also don't impose transfers. A can be a pair of qualities and transfers, but it doesn't have to. A could be a match, A could be a candidate. So the setting is not restricted to settings with transferable utility or to settings where we have time separable payoffs or discounting. Any payoff structure works, any set of allocation works. In the math got really messy in the paper because this space we take it to be, the set of current allocations is taken to be a Polish space. So you can take this to be finite, a continuum, whatever you want, as long as it's a Polish space. Are you with me? All right. Okay. So now, what is the set of mechanisms that determine a period by period interaction? So we're going to write down an extensive form, and we're going to assume that designer is choosing a mechanism that has this form. It consists of a set of input messages M, a set of output messages S, and a mapping that will map an input message to distributions over output messages and allocations. So N is a set of input messages, and we're going to assume that its cardinality is greater or equal to the cardinality of the type space. So if the type space is a continuum, M is a continuum. If the type space has 1 million types, we are going to allow the M to have at least 1 million messages, and then S is a set of output messages. So these are
just to make sure. So the output
Please.
message is the public information.
I'm going to write down the timing and what is observable.
Okay.
Yes, but because we are in a lecture and we're going, yes, it's public, and it's important that it's public.
Okay. Thank you.
Because you could also think about the output message being a message for the agent and a message for the principal.
Yeah, right.
That will create the issues that I was alluding to earlier, that we don't know what was the output message.
Right.
But now, think about, so an intuitive way to think about, actually, let me proceed the way I planned it now. So this is a short-term mechanism. So in contrast to some other works that talk about smart contracts and so forth that you might have seen in the literature that were published subsequently, this mechanism does not depend on past input messages, since the principal can offer only spot mechanisms. So the principal tomorrow knows only the past output messages and allocations, but not the messages that were inputted in the previous period, and the mechanism cannot be carrying on past input messages. Every period has to depend on current input messages. Make sense? Yes.
Why are you assuming this thing? Practically, it's possible for me to depend my second period mechanism on the first period input mechanism.
Yes.
That's what you exclude. It seems. Is that what you said?
Yes, we are excluding the current mechanism to be dependent on past input messages, because if we start introducing...
Who saw the first period input message? Is the mediator or...
There is no mediator here. So this is a relationship. So here we're trying to... You could, of course, think about a more rich contractual environment where you have a mediator collecting messages from the agent and then maybe suggesting mechanisms to the designer today. But this is a different time. This is a different set. This is a different natural extensive form game. That's not the one we studied.
So in the first period, there is an input message, right?
Yes.
So who saw this input and implement first period mechanism? Is it mediator or
So the principal chooses a computer.
Yeah.
You put your type in a computer, and the computer spits an output.
I see.
So imagine the computer as being a garbling device.
Okay.
So I'm putting my message in. I am seeing the design. I can choose a computer that actually tells me what is the M, and then I will select.
Okay.
Yeah, tell me. Yeah, so that's
like fast.
Yes, but of course there are many other ways to think about mechanisms and imperfect commitment. This is the thing we thought is the most natural, given the work on spot commitment of Lafontaine. Okay, so this is exactly the timing they were thinking. Okay, so now because this is what the designer is choosing every period. So this is a function, this is a complicated space. And to make the designer's problem well defined, we are going to assume that there is some exogenous collection of messages. So now you're writing a game. Usually when we write a game, we write down, this is the action set for a player. Here, the action set of a player consists of these functions. Are you with me? To make the selection, the choice sort of well-defined, we're going to assume that there's some arbitrary collection of messages. Because zillion, collections. This has many, many, many elements. But you can choose an input messages and an output message space from any mapping phi measurable from M to distributions over S, Sj, comma, the allocations. Are you with me? The collection doesn't mean anything. It can be an arbitrary collection. We're just making this assumption. This is not really an assumption. We're just writing this way to make the choice well-defined. Yes.
So you're going to focus on this type of mechanism and give us the real revelation principle.
Yes.
Okay, so there could be other mechanisms that fall outside of this class.
Yes.
Where the relation principle may or may not fall. This, so that I understand where you're going.
Yes. So this is actually, you're correct, but not. Let me change your words a bit. So the revelation principle we prove says if you are studying this, any type of dynamic relationship of the form I just wrote down, with these mechanisms, our mechanisms replicate all outcomes. If we have a different extensive form, in particular one where the designer is offering mechanisms that can depend on past messages, we could have outcomes that we don't replicate with our mechanisms. So there could be different outcomes. We don't know if it's going to be, and in some games, we know, for example, from the work of Tapuro, that in like Barry Seller, or the work of Georgiadis, Burkowski, and Zentesh, that if you allow for smart contracts, like contracts that have some memory, and there is a mediator operating those contracts, the mediator introduces some intertemporal commitment. Because the mediator can sort of store information for you and keep you from accessing it if you're deviating. So when you have those type of richer contractual spaces, you can do more usually, although it's not 100% clear. And actually those papers, they've been trying to prove revelation principles along those lines we have, but to the best of our knowledge, we don't know of any analogous results at the moment. That doesn't mean they are not possible. It means that they have not been formulated. But, so if you buy a notion of limited commitment, which corresponds to the notions of Lafont-Tirol, this class of mechanisms that I'm going to give you are replicating all outcomes of that particular game.
So just
Yes.
in case, so I'm a bit confused about what you mean by the short-term mechanisms.
Yes.
So you say like so in period 2, I have to choose a mechanism.
Again.
Right? Then so the choice of the mechanism I'm giving to the agent
Yes.
does not depend on the first period input message. Does it what you mean?
Yes.
Okay, I see. So that means like so you say like but still what happens in the first period actually gives me some extra information about. So that does that come from the output messages?
Yes.
Okay,
And
so-
the allocations.
And okay, so the allocation is also information.
Yeah.
Okay,
But let me look. Let's discuss the timing.
Yeah.
Okay? So first of all, the agent has learned their type. I did not put that in the timing. Okay, the agent knows theta, and then we are in period T. Now the principal and the agent observe the realization of a public randomization device, and I will explain why we need this logic. Okay. The principal offers the agent a mechanism of what I just told you. All right. Then, observing the mechanism, the agent decides whether to accept the mechanism or reject. If the agent accepts the mechanism, the agent privately reports a message M, and then S and A are drawn from phi, and this is publicly observed. All right. These are the questions that you were already asking. If the agent rejects, and then we move to period T+1. If the agent rejects, then the allocation A star is determined, and we move to t+1, as you asked. So this is the timing.
Oh, so maybe this is obvious, but when you say the agent privately reported, does it mean that the mechanism designer does not observe M?
Exactly.
Oh,
So can you actually specify the history of the information for the principal? At the
Yes.
period T? Okay, good.
Yes, yes.
No, it's good.
So, yes, so bear with me 1 second. Yes, you are right on this. You are really very attentive, and I'm really grateful. So the above defines a mechanism selection game G, where we can index it by I should have put the collection of messages here. I was changing a little bit the way we had presented this in the past. So this collection here should be indexed by the collection of messages, all right? So the public histories are as follows. This is what everyone sees. We see the lottery at the beginning. Then there is a choice of mechanism M1. No, these are not the messages. This is the mechanism. It's supposed to be bold. It doesn't look like bold, but it's different from the mech. Okay, this is the mechanism. Then pi1 is the agent's participation decision. And then we see S, the output message, and A1, the participation. So if you don't participate, this output message is the empty set, and this is a star. But to not to make the notation a mess, we just say, we see whether you participate or not. So that's the public history, all right? The private history of the agent, indexed by HT of A, is the same as the public history, but in every period, the agent knows what they report in the mechanism, which means that the agent here accumulates private information. Because in period 100, I know theta, and I know the 99 messages I said in the past. And this is not known by the designer. So now the designers believe at history T, given some public history HT, are beliefs about theta and about the private histories of the agent, which are consistent with this public history. And notice that the public history itself contains a lot of information, because the theta, which is inputted, which the theta determines the M's that go into the mechanism. The M's that go into the mechanism determine what S's and A's I'm seeing. So this contains information, but not directly the M's at this point. Is this better now?
Yeah, right. No, it's good.
Okay. Yes, I could not start with this slide though. I had to.
Yeah, right, yeah.
So now what are the strategies of these players? So the principal strategies at every history describes the possibly random choice of mechanisms. So the principal can be mixing over mechanisms. And the agent strategy when they are typing theta, this history, and given this mechanism proposed at period T, it specifies the probability of accepting the mechanism, and the reporting strategy, which specifies the probability distributions over the messages of the mechanism proposed. All right? So now we're going to be thinking about, so these are the strategies. We have our histories. This is a game, a dynamic game, and we're going to be thinking, we're going to be focusing on assessments of this game that are perfect based on equilibrium. And I'm going to write down informally the definition. The definition fully fledged is in the paper, but the PBE requires that the principal and the agent strategy are sequentially rational, and that beliefs are determined by a base rule whenever possible. So what is an equilibrium outcome here? The prior mu1 and the assessment sigma p, sigma a mu induce a distribution over the terminal nodes of the game. And then we project those distributions onto the set of types and A of T's. Okay, so we get the distribution over terminal nodes. This is a game, complicated game, but we project those terminal nodes onto the thing that we care about, which is types and allocations. And the problem is to replicate outcomes, the mechanisms we are thinking are encoding not only the rules that determine the current allocation, but also the information the designer obtains from the interaction. And that's sort of the role of the output messages. Because the output, if the mechanism is fully revealing, the M is invertible. So I can learn the M from the S, but I could be garbling the S, so the M. So for example, I could be putting all M's to one output message and then one allocation. Then I learned nothing. It's like a full pooling mechanism, if you like. But with the revelation, with the standard mechanisms we have, where we're thinking about each message being fully observed, we are sort of tying our hands a little bit. And that was what was initially done in the literature. So let me start with a little bit motivating where do these mechanisms come from, right? Because they look like, please, of course.
What about off-path belief?
Excuse me?
What about off-path belief?
Of course. So off-path beliefs are going to be an important part of this problem. So when I say we replicate all outcomes, a lot of the work we had to do in the proof is what happens in off-path where we have where beliefs are not being done by Bayes' rule, and we see messages that are run with probability 0. All of those things have to be taken care of. So the way the proof works, you are going to see at some point that we guarantee participation only for types that have positive probability. And this is some of the detailed work that had to be done to be able to replicate all outcomes with this very coarse language of beliefs. So there are going to be, but we have worked with taking care of everything of path, all messages that have 0 probability, because when we replicate, when we take this fully extensive on game with all these histories, a lot of them are never arising in equilibrium. We have to specify play everywhere, and the specification has to happen with our class of mechanisms. I won't have time to tell you about all the details, but I just want to tell you, to reassure you that we have dealt with all of this.
By the way,
Yes.
probably that's gonna coming up sometime soon, but does the governing actually helps the mechanism designer?
Yes.
Okay, I see.
Yes.
So that's why you wanna say.
I mean, it's not that we want it. Let me explain where you mean.
Yeah, okay,
You're always 2 or 3 slides ahead of me.
okay.
So that's great for you. Maybe it's frustrating because you are quick and you're still like, when is this going to say this? I'm sorry, but we're gonna get there.
Okay.
Okay. So let's think about the mechanisms we see in Meyerson's 1982 paper and related works by Forge in the 80s. So I guess this is not 100% a fair comparison because the model of Meyerson is a model with multiple agents, and he allows contractible outcomes, which means that there are the A's that we talk about here, but he also allows for fully non-contractible decisions or actions that are these actions that the agent can be choosing. So all of those things, we don't have actions, we don't have many agents here. Are you with me? So we don't have moral hazard in particular in this model with LoRa. We only have contractible decisions. So in Meyerson's paper, there is a set of input messages and a set of output messages. And phi assigns to each input message a joint distribution over messages and allocations.
What's the assumption on M and S? Are they just the Polish spaces?
Yes.
Okay.
And they have some constraints on the cardinality. So we assume that the type if the type space is finite, for example, and the set is finite, then it has to have more types, more messages than types. And also we assume that the collection in the extensive form the output messages also contain the set of beliefs about the types. Yes. Okay, so the way these mechanisms work, the agent as a function of the type sends a message, the message goes into phi, and then with the principal sees S and A. So the revelation principle under commitment says, without loss of generality, communication is direct, so messages equal types. Communication is observable, M and S have the same cardinality, so phi is invertible, and the output messages are redundant due to full contractibility. So when we have full contractibility, we don't have basically any actions like an effort. We don't need these output messages. We just think as M and S being the same thing, so that means the phi is invertible. So I see the S, I know the M, and communication is truthful. So when we have full commitment, we just say the mechanism is a mapping from theta to distributions over ultimate allocations. Yes? Now, Besser and Strauss is the first paper that I was alluding to that wrote the revelation principle in these settings. So they look at a setting with one agent and has finitely many types, and they assume from the get-go. They look at the mechanisms along the lines we wrote, but they have some even further restrictions.
That's it.
Yes.
Sort of lost in the last slide. What was the revelation principle?
This is under commitment.
Under commitment. Okay.
Under commitment, we will get
I
X
see.
equals
Under
theta,
Okay.
and communication is observable. So
This is the
we are going to have an invertible phi. So we got the S is, and because we have full contractibility, the S is redundant. We don't have any S. We just have a mapping from theta to distribution over A's. That's the revelation.
So under commitment.
Under commitment.
Yeah.
Now we move to the first paper with limited commitment, Besser Strauss. Here, those authors, they start with a class of mechanisms that is even more restrictive than ours. That's how science progresses, though. This was a big step. I mean, science is step by step. They start by assuming communication is observable. So M and S have the same cardinality and phi is invertible. They don't allow for randomization in the allocation. So that's actually a big restriction because we need the randomizations. So each output message or input message in their case is attached to one allocation. So A of N. And then they also have a reduced form way to capture limited commitment, which means that the principal observes M because it's observable, updates the beliefs, and then chooses YM that maximizes his payoff in the second period. So there is only like a 2-period interaction, and the second period is a reduced form way to capture limited commitment. And in that sense, they don't even write down an extensive form, so they don't have to deal with histories, off-path, or any of that. And that is important because in some of the games, a lot of things can happen when you allow to not optimize. You can, like in repeated games, that here they are well expert on repeated games. A lot of the good outcomes are sustained precisely by having suboptimal play specified in some nodes of the game. All right.
So
Oh no, I
sorry,
went back. Please, yes.
So yeah, here are you assuming that there are 2 periods?
They are assuming that there are 2 periods.
Okay, so
We are assuming.
no, this slide.
Yes.
2 periods. Okay, that was my question.
Yes. That's what they
Yeah,
have the
2
main.
periods.
So the body of the paper is written by these 2 periods, and then they have an extension to multiple periods. But that extension, in our view, is kind of problematic because it imposes some Markovian structure, which is with the loss of generality. Okay, so under those assumptions, so first let me say some things. So the fact that communication is observable is no longer without loss of generality due to limited contractibility. So although in the revelation principle at a commitment, we got that full observability is fine. Let me go back because with at the revelation principle under commitment, the M and we can assume that communication is observable because you commit to it. So you'll see, I see your type, but I have already committed what I'm going to be doing to your type, and then that's it. When we have limited commitment, communication is no longer observable communication, no longer without loss of generality due to limited contractability, because the principal only commits to the data allocation. So what these authors show is that under those conditions, so observable communication, no randomization, and reduced form of limited commitment, if the principal earns his highest payoff, consistent with the agent's payoff, then without loss of generality, communication is direct. So they are thinking about the Pareto frontier of payoffs, not all payoffs, not all outcomes, and they are showing that we can replicate the frontier with direct communication. However, we're going to lose truth-tellingness. That's the revelation principle of Besser and Strauss. So that's still a simplification because before researchers, they were trying to do two-type models, and they thought, how many messages do we need? Do we need 10? Do we need 20? This result said, look, you need 2. That is a big result. But if you have 3 types, you need 3. And if you allow for mixing and you have more than 2 types, good luck. Because each type, in those settings, you can be mixing upwards and downwards, actually. So how a player is reporting is not pinned down by this result. And of course, these authors are very smart, and they realize, oh, why did we assume this? But, let me kind of also tell you some background. At this point, the intellectual background is more the Toulouse approach of mechanism design, where there's a lot of taxation principle type of arguments and not really thinking about the communication. But they started reading Meyerson 82, and they said, maybe we should start using the mechanisms in Meyerson 82, where the information, there is some communication in the mechanism. So then, in 2007, they published another paper. Sorry, it doesn't contrast very well, something happened. But this is Besser and Strauss 2007, barely visible, but hopefully, given that I'm saying it somewhat. So this is sort of the second version. So now they're adding nodes to the communication. That's a big innovation. So now they remove this assumption of full observability, and they maintain the assumption of reduced form commitment. But now the principal just observes the output message, updates and chooses a Y of S that maximizes payoff. And they maintain the assumption of no randomization in the allocation, so each method is attached to one allocation. And they show under those assumptions that without loss of generality, communication is going to be direct and truthful. So that's a big second step of progress in science. We started with 2 types, no idea how many messages we need to have. First big result, Besser Strauss 2001. Well, you don't need more messages than types if you have finitely many types. Second paper, but this paper had the problem, the 2001 paper had the problem of, well, we know the messages, we don't know the behavior. So I want to kind of pause here because a lot of students in the lecture. The revelation principle is not just about canonicity of the class of mechanisms. It's not tell you play second price auction. It tells you how to play the auction. It tells you canonical language, rules, and play. 2 things. And that's why it sort of nails the problem, because it tells you, look, you're going to look at second price auction. I'm just making it like a specific class of games. Let's call it direct revelation games. And it tells you exactly what behavior can be expected. Here, the first paper did not pin down the language, but not the behavior. The second paper did both. So why did we write a third paper? Well, we don't know still. First of all, there are 2 things here. There is a reduced form of capturing limited commitment, 2 periods, and we don't know what are the output messages. But the output messages are what is needed for the current allocation and for the future allocation. And this paper did not say what those are. Are you with me? So now, this is where we come in. So our result says, for the extensive form I wrote down, so now we are in a fully specified game. So we are going back to the original game with the histories we wrote. Are you all with me? And everything. And now we show that communication is going to be direct. And this argument, the first step of the argument is like the one in Besser-Strauss 2007. But our argument is a bit harder because the agent accumulates target information. And communication is direct here. And notice my type is, I'm always communicating theta. I'm not going to communicate in period 20, M1, M2, M3, M18, and theta. I'm only communicating the payoff relevant type, not the things I was saying before. So this is, so the canonicity of this language, given the extensive form we wrote, is not so obvious if you're thinking about, down the line. And then the output messages in every period are beliefs about types. So now, and equilibrium is truthful. So equilibrium output messages coincide with the principal equilibrium belief. So we have the meaning of the message. There is literally, the messages that are communicated have literal meaning. So they have the truth, and the output messages are literal. And the fact that we're insisting on having output messages being literal is what is very delicate to deal with often, because we cannot assign whatever, because the beliefs are a big space. It has a lot of cardinality. You can embed any space you want in this space by losing the literal meaning of it. But if you want the beliefs to have a meaning, that also ties your hand a bit. So, okay.
Can you share a thought? So,
Yes.
So from these things, on the equilibrium path,
Yes.
does this actually mean that the principal learns the type at the end of the period one?
No, because he doesn't see the type.
Okay,
He will see.
Maybe I'm confused. So the equilibrium communication being truthful.
Truthful, but let me pause here. The communication is not fully observable. M is not observable. What is observable is the output message.
Right. So sorry.
So I'm not going to learn theta. I'm going to learn the input. So this is M. I'm not going to see M. I'm going to see the beliefs about theta and the allocation.
Yeah.
And
sorry. I thought I misread the slide. Now I think I understand.
So this is what I've told you so far is that the mechanism can take input messages theta and spit out beliefs and allocations. But we also prove another thing. We can decompose it. So this is a transition probability. It's theta. It's a kernel from theta to beliefs and allocations. We can decouple this transition probability into two transitions probabilities. One from theta to beliefs, and then one from beliefs to allocations. So basically, let me pause here. Suppose you had a mechanism that is full pooling, okay? The theta is going to be mapped to the prior, and then I'm going to map the prior, the single thing, to a quantity and a quality or a match or something. If we had a fully separate, if we have each data mapped to the Dirac measure, that's like a direct mechanism because I'm mapping, suppose I have two types, which I can separate even under limit commitment. Then I have one type mapped to the Dirac on itself, each type mapped on the Dirac on itself. Then the alpha, the allocation, is going to map the Dirac on allocations, which is like the direct mechanism. So the direct mechanisms the direct revelation mechanisms are a special case of this class of mechanisms where that each theta is mapped to the Dirac measure on itself, and that's it. Do you see that?
Yeah, and is it actually the consequence also for the the false property? Because again, the false property means you do not learn from the A, right? If you have the
No,
same,
you learn from
know,
the A. You learn, but the learning from the A is already encoded.
Yeah, it must be already encoded, so that means
In the
you effectively you do not learn from A,
Effectively, you don't learn from
right? So
Yes.
that's
So basically, that's what we do is basically the way that the proof works is you take all of those histories
Yeah.
and then you orthogonalize everything.
Mhm.
You basically, and that's also some kind of, it talks a little bit how why we need the reason we need the public randomization device is to play with kind of mixing
okay.
and to orthogonalize the information. So we take the histories and then everything that is non-Bayes relevant can be dumped into this omega.
Yeah. Okay.
Everything that is theta
I see. That's more complicated than what I thought. Okay.
it's a bit complicated for
Yeah,
the lecture now. So I'm not saying all of those things in the
Yeah.
lecture because this proof is,
it's very delicate. Yeah.
It took us like years to do this. And maybe other smarter people can do it shorter, but it took a long time to do this.
But question?
Yes.
Are there any restrictions on the dynamics of the beliefs? If it's belief on theta, is it going to be martingale or something?
No. Well, of course, it's based, this basic plausibility.
Yeah.
Yes, of course. They are everything, all all the restrictions that come from Bayes rule.
So it shouldn't happen that in period 1, I believe that the theta prime is true with probability 1, and suddenly in second period, I start to believe that the true theta is theta double prime with probability 1.
That will not
That
be
could-
possible.
Yeah.
For Bayes rule.
So there should be, okay, so Bayes rule, okay.
Yes.
Belief
So-
dynamics
Oh, no, there's.
won't be equilibrium path.
Yes, so I'm going to talk about all of these things in a minute. Yeah, yes. So, these mechanisms, because they are eventually decomposed into mappings, and this is like an experiment. This is, if you think about Kamenetz-Gensko, what we think about an experiment mapping the state space to distribution over posteriors. Now, our mechanism has an experiment and has an allocation rule that maps the belief to our locations, and that's why we call them direct black hole mechanisms.
Can I ask one? So here, if there were no output messages, then the belief is a private information of the principal. Is that right?
If there's
no output messages in the second breadpoint,
yes,
then the belief is the private information of the principal. Is that right?
but here we are assuming that, yes, that's true. That's
Okay, I see.
It is possible. It is, yes. So that's a version of the problem we did not analyze. And we also, did that because we wanted to be, yes. So you could have a mechanism where there is an output message observed by the principal and an output message observed by the agent, potential. So then the agent does not know what are the beliefs of the principal by himself. That's a very natural thing to think about. We have not thought about this. The reason we haven't thought about this is not that we didn't think it's interesting, is that we didn't want to start writing a problem where we had to deal with limited commitment and with privately informed principle. So in Bonn, if you're interested in informed principle, last week I gave 4 lectures in Bonn on the topic. They're also on video. And informed principle is not an easy problem either. So we wanted, when we started with Laura, we said we're going to do one thing at a time.
Yes.
So this is the one thing we did. And that's why the messages are public. But it's also very natural. Like, I don't want to defend this. We did not do this because we thought this is simple. We thought this is a relevant benchmark.
I see.
So in a situation where you're thinking about an auction. So when I started working on my job market paper limit commitment, I had a very specific motivation. I was not a very highbrow theories as a student. I was a student who went to seminars and saw all these game theories presenting about designing of the FCC auctions. Milgram was coming, Peter Crampton. They were really thinking about how the FCC should sell the spectrum. And they were thinking about efficiency. So I was thinking, why do they really care about efficiency so much if in a market, you sell something, and if someone values it more than the buyer, they will just buy it. There's going to be trade. So I was thinking about resale. So initially I started thinking about resale, but then I thought, well, there is a step before resale. Suppose I am the FCC and I start to sell it, but nobody buys it. What happens then? So in an auction, when you are, let's say, a government privatizing a company, like my country was asked to sell all its assets a few years ago because Greece was almost bankrupt. It's not like, Japan where it's a strong economy. So if you are a seller and you are selling a company and you run the auction, you see what happened. There is some common knowledge of what happens in that auction. And then you come back and you want to design another one because nobody won the competition. At that point, we assume that if there was only one firm trying to acquire the asset, it's very natural that the firm and the seller know what happened, and it's common knowledge. So that's what we're trying to capture here. Sorry for the long parenthesis. All right, so let's go back to theory now. Okay, so let me recapitulate what things have been already saying. So as I said, a direct black hole mechanism consists of a disclosure policy, mapping types of distributions over posteriors, and an allocation rule mapping posteriors to distributions over allocations. And as I already said, direct revelation mechanisms are a subset of direct black hole mechanisms. Why? Because a direct revelation mechanism simply maps each type to the Dirac measure. So that beta mapping is basically the identity. Theta goes to delta theta. And we also get canonical behavior. With our result, the agent's behavior is reduced to participation, truth-telling, and base plausibility constraints. And our result replicates all equilibrium outcomes of any mechanism selection game among the class we wrote down, not different classes. And this is crucial for infinite horizon settings. So now I want to kind of contrast a little bit mechanism selection games versus mechanism design. So in standard mechanism design, the principal is a designer who commits to the rules of the game and commits to the equilibrium selection. So if you read Meyerson's 82 paper in Meyerson's book, he says mechanism design is a sort of blend cooperative, non-cooperative and cooperative approach. It's cooperative because we are sort of selecting the equilibrium as well. That's what he writes. I know that some of you work on cooperative solution concepts, and hopefully the comment is not very confused. But in any case, in standard mechanism design, we commit to the rules of the game and the equilibrium. In a mechanism selection game, the principal is a strategic player. So there are three consequences. First, a smaller choice set can help. So restricting the menu of admissible mechanism ties the principal's hand and can improve outcomes. So I don't know if you know about Odyssey, which is a Greek ancient. Ulysses tied himself on the boat so he doesn't get attracted to the singing of the sirens. So when you have limited commitment, it's good to tie your hands. Optimizing in every period can hurt. So the principal optimal PB may require continuation play that does not myopically maximize her payoff. And that's why characterizing all equilibrium outcome matters and not just the efficient ones. And that's the big contrast with the Besser and Strauss papers as well. So it's not just that we get the output messages, we also we replicate all equilibrium outcomes. And sometimes, someone asked about that already, less information is better. Noise and pooling in the current mechanism reduces the principal's future temptation to re-optimize. So if I know you're going to basically exploit me, I am not going to behave in a revealing way today. But if there is a way to prevent myself from being revealed too much, then that gives me more, makes my behavior loosen up a bit. So now noise or pooling in the current mechanism reduces the principal's future temptation to reoptimize and alleviates the ratchet effect. So contrast with commitment. In standard mechanism design, larger design set is weakly better, more information is weakly better, and design is equivalent to optimization. That's not necessarily the case in a game. However, after we have a revelation principle, we can sort of turn the search of the optimal PB into a constraint optimization problem ultimately. So we do get, yes, please.
Oh, so,
No, please.
so at this point, what's the intention for that result? So is it possible to get?
I'm going to show you a very contract example. So this is an example. So there's some history behind this example. So that I had also some discussions for the volume that you asked for the paper, and we had a lot of back and forth about whether at least in this optimization in the second period is without loss, blah blah blah, and what it's a. So here I wrote an I wrote an example that is a bit contrived because I wanted to make a point of how naively thinking about the principal optimizing in the second period, how it can be bad, and how restricting choices can be a good thing. Okay, so I'm going to illustrate the 3 points in the previous slide with this trivial example. So the example has two types, so it has two periods, and two types, 1 and 3. So the period 1 outcome is a probability or a quality of trade Q and a transfer. And the second period allocation is some number between 0 and 1. So you can think of some harassment, possible harassment. So the agent's payoff is theta times Q minus X if the harassment in period 2 is going to be 0, otherwise it's 0. So think about I'm going to choose a gym and I'm going to consume Q and pay X today, but I don't want to be bothered every period, next period about buying personal training, blah, 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 something extra. I just want to join and not be harassed. And if I'm expecting harassment, I'm not going to join. That's sort of like now the principal's payoff, he gets some money in the first period, and then he gets a payoff that depends on the level of harassment, the expectation about the agent's type, and divided by some number K, which is greater or equal than 3 or something. So now, if the agent joins in period 2 and he has no commitment, he's going to choose the thing that, so under commitment, first of all, I did not write on the slide, under commitment, the optimal thing to do is to select A2 equals 0, and then max, because no matter what you do, you're never going to make a lot of money in the second period, and under uniform prior, it's better to ask a price of 1.5 and sell the good only to type 3, because that's the commitment. You have two types, it's 1 or 3, they're uniform. So if you sell to both types, you're going to make 1. If you sell only to the high type, you can sell at price 3, with probability of half is 1.5, and you are selling at price 3, and you're committing not to harass. Suppose now we have naive sequential rationality, and the principal maximizes in period 2. So in period 2, you have forgotten about period 1, because now we're in period 2. Now you're going to choose A2 equals 1 here. No matter what your expectation about type, you're going to just choose the A2 that maximizes this term. So there's a unique naive optimum. Choose the highest possible level of harassment once we're in period 2.
Question?
Yes.
What's the role of expectation theta multiplied by A2?
This is just,
expectation is always positive, right?
yes, this is just.
Why do you need this expectation term?
Oh, because I just said no matter what you learn in the first period.
It's always positive, right?
Yes, it's positive. Exactly, it doesn't matter. So I could have,
you just cross out the.
you can cross it out.
Okay, okay.
This is maybe I could have made it the example nicer. So sorry.
Okay.
Or maybe in the paper, maybe the chapter is nicer. I don't remember what I have now, but yes, it doesn't matter. Your payoff is some a
Increase in
increase. Yes, you're right. Thank you. So, I had a time deadline. I'm joking. Yeah, so maybe I should have made that. So in any case, so notice because the agent now, once we're in period 2, the agent doesn't really care about the A2. He, at this point, rejecting any mechanism is also a continuation equilibrium for the agent in period 2. So if the, once the agent is in, the A2 does not matter for the agent in this specification. So rejection is the best response, which is equivalent to selecting in my modeling A2 equals 0. So when we specify continuation equilibrium where the agent rejects the second period mechanism, no matter what is the proposal, the principal's payoff is 1.5 and we get the commitment optimum back. So what are the lessons from this example? Naive sequential rationality is not the same as PB feasibility because it imposes a Markov restriction, which is with loss. Multiplicity is a feature. When we have a continuation equilibrium where the buyer rejects no matter what, the principal can select this continuation equilibrium, this rejection, because it works as a restraint, because it essentially works as a restraint. And the smaller choice set helps. If the choice set of the harassment policy was a priori restricted to just 0, then we would get the commitment outcome even under this myopic optimization, because we would tie the designer's hands in the second period not to harass. So that's the things I wanted to communicate with this kind of example.
What was the first bullet point again?
This one,
Yes.
the naive sequential rationality. So assuming that the principal maximizes payoff in the second period. So in the Western-Strauss approaches,
That's what you're gonna do, right? And
that's
so-
what Western-Strauss were doing.
And then that means the agent's never gonna join the gym.
Exactly.
And so you're stuck with 1.5.
You're stuck with 0. Because
Oh, yes, you're stuck with 0, exactly.
yes, because if the agent anticipates harassment, they never join.
Yes, so you're stuck.
So the agent, if we think about the agent, if we specify continuation play, that the agent rejects no matter what is the mechanism, and so the agent, then the principal will set A2 equals 0 because that's an equilibrium. Then we can sustain commitment under the specification of continuation equilibrium.
And then the PB feasibility, so that's.
The PB feasibility is that it's a continuation equilibrium for the agent to reject anything. So then I'm going to offer A2 equals 0 and rejection as the best response. And by specifying that play tomorrow, we are basically achieving commitment as the PB. Does it make sense?
So I guess if you have naive sequential rationality, the principal can only get 0.
Yes.
And then you're saying that first bullet point is saying that's not equal to PB feasibility.
Yes.
And so, sorry, what was the PB feasibility?
Because PB feasibility is to think about all continuation plays, and then select the one that is best from the examiner perspective.
For the principal.
For the principal.
Yes.
So I'm saying that when you're thinking about this more as a strategic setting and you allow for these multiplicity in continuations, this can be a feature because it can help you get the commitment, which was something that Western-Strauss work did not show because they were always assuming that the Y of M is optimal given the M.
I see. And this PB feasibility involves setting this A2 or the action that the principal can take in the second period to be equal to
0 and accompanied with rejection. So A2 0 and rejection are mutual best responses. So when the buyer says, I'm rejecting no matter what, A2 equals 0 is the best response for the principal. Yes. Okay. So now let's look, how much?
You have 15 minutes.
Okay, perfect, good. So let's talk about the theorem. So the theorem says for any collection of messages calligraphic I and any PV assessment of this game indexed by this collection of messages, an outcome equivalent public. So there's something I did not stress so far, public PV, and I will explain in a minute, of a game where the messages are theta and G and output messages or beliefs exist such that after every history on and off the path, I know you like off the path, the principal offers a direct black hole mechanism. In response to the principal's equilibrium offer of a mechanism, if theta is in support of the principal's belief at HT, then theta always participates. Conditional on participating, the agent truthfully reports her type. If the mechanism outputs belief mu, then the marginal on theta, because remember the beliefs are about theta and the history, but the marginal on theta of the principal's belief coincide with mu, and we call a PB assessment that satisfies the above properties a canonical PB. So canonical PB of the canonical game, so we have a canonical PB, which means this behavior. The canonical game is the extensive form game where now we don't have many messages, many collections. We have one collection. Inputs are type reports, output messages are beliefs. So this game is much coarser than the class of game we started. And this play is also much coarser and public. So canonical PB of the canonical game replicate all equilibrium outcomes of all mechanism selection games in this family. And like the standard revelation principle, it reduces the agent's behavior and its impact on the principal's belief to a series of constraints that the mechanism must satisfy. So truth-telling and participation, which is the standard ones, plus base plausibility constraint, which is the constraint that keeps track of the designer's sequential rationality. All right, so that's sort of the theorem. I'll let you pause for a second.
And by the way, so we are just interested in the equilibrium outcomes, which is just the whole sequence of the AT. We are not concerned with how the information is revealed through the path. Is this right? The ultimate outcome. So we might also be interested in how the information is gradually revealed to the the principal potentially for the different mechanisms. Probably that can be replicated.
It could, yes, probably, but I guess you care about the information because essentially you care about the allocation.
Yeah, right.
So if you have but there are some
I'm not trying to criticize, but I just want to understand.
Sorry if I responded in a way that it sounded like a criticism.
Yeah.
I just wanted to add on what you said.
Okay.
If you had a setting like a psychological game, in a psychological game, beliefs, like if I'm the agent and I care about the perception of the principal about me. So like my daughter now that we are in this country and everyone is polite, says, Mom, please don't embarrass us. You have to be for you. She was reading about the etiquette and she cares about how people perceive. So that is a very natural environment. In this game we wrote down, we did not assume people's payoff depend on beliefs. So by replicating A's and thetas, we replicate payoffs. In a psychological game, you might want to actually replicate the beliefs because that's actually something that is important. So here we replicate the allocations. Okay. And I want to also say something about the publicity of the PBE. So at some point in the proof, which we show that with all of the generality, the agent's behavior can condition only on public histories. So the agent's behavior depends on the agent's history. The agent's history have all these messages the agent has been saying all along. So we show that actually we can replicate behavior when the first proposition in the paper is to show that we can replicate everything with behavior that depends only on public information. And the intuition for that is that if we have, suppose you are type 2, your type is 2, and you have two histories that include all these past messages. And just to make it visible, one history is the red history, one is the yellow. Suppose all of those histories are your private histories that they are projected on the same public history. So the allocations and what the principal has learned about you are the same in the red and the yellow, which means that you have in the past consumed the same things. Now, if you are using different behaviors for these private histories, you must be indifferent in the future because they are both best responses and the payoffs are the same in the past. So if you're doing different things, you are indifferent. So we are using this indifference to build an outcome equivalent public history. And that's how we get another property, which I did not stress so far, which is the recursivity. But let me say what our revelation principle allows us to do. Like in mechanism design, the principle of the equilibrium choice of mechanism satisfies participation constraints and incentive constraints. Like information design, which a lot of us know, consistency, we get consistency between output beliefs and equilibrium beliefs because we insisted that our messages have literal meaning. And then we have two implications. The principal's belief plus the communication device of the mechanism induce a base plausible distribution of a posteriors. And in the applications, we can separately design the information and the allocation. So in some settings, with transfers, for example, we can get the virtual surplus representation optimized with respect to Q to the allocation probability for each belief, and then do information design. 2 steps. And the fourth thing is that that comes from the public PD, we get recursivity. And this is super nice when we have infinite horizon problems. So because of all of these things, we have done some new applications. Because we don't have cardinality on reciprocal cardinality of the type space and the length of the horizon, we also have an extension to Markov settings in the sense of Markovian types, information evolving in a Markovian sense. We have been able to show that prices are optimal in an infinite horizon binary type durable good model. So in my job market paper, I had finitely many periods, but a continuum of types. So actually that problem is still an open problem with more general mechanisms, the one I did in my job market paper. And we are going to show you how we can do the product line design in the second lecture. So we are able to show that limited commitment, when we're thinking about a monopolist choosing varieties or choosing a nonlinear pricing, like in a Musa-Rosen setting, we are going to show that limited commitment actually coarsens the menu of varieties that the seller uses. And then to use this framework, because we are introducing information design with additional constraints, we have developed a paper which was published in the Mathematics of Operations Research, which is called Constraint Information Design, where we derive some results that one can use to solve complex information design problems under arbitrary number of inequality or equality constraints. Okay, so someone shared this to us, and I thought it was very funny. So this is Besser and Strauss, which is there you get live, but not your live, but continue. Whereas in our case, you tell the truth. And I love listening to lies when I know the truth. So I hope you don't mind me adding this. But when they shared it to me, I thought this is so funny, and I have to put in the slide. All right. So we did not do that. Pablo's can only do that. All right. So we have about 10 minutes before the break, I think, right?
Yeah.
So let me start telling you about how direct black hole mechanisms work and how we use them to replicate outcomes. I'm going to show you basically a sketch of the proof and how to use the result in the simplest possible setting one can imagine, which is a durable good setting with two types and two periods. It doesn't get easier than this. So now we are going to specialize in many ways, but please don't think that the model only applies to durable goods, because sometimes I read papers writing, citing our words and say our paper, relies on transfers, whatever. No. So the durable good is just an illustration. Don't the model. Okay, so we have a buyer and a seller interacting over infinitely many possible periods. Possibly, we're going to do two periods in the example. The seller owns 1 unit of a durable good and assigns 0 value to it. The buyer has private information that is either low or high, and the probability that it's high is called mu. We also discuss in the paper the case where the types are a continuum and theta is drawn according to F1, but I chose a different application for the second lecture. So a current allocation here, A of t, is just a pair which specifies Q and X. So Q is either 0 if we have no trade or 1 if we have trade, and X is a real number. So Q indicates whether the good was sold or not, and X is the payment from the buyer to the seller. If the good is sold in period 2, the game ends. And if the final allocation is A of t, which specifies whether the good was sold or not, and the transfers, the buyer and the seller's payoff are now, we have discounting and we're summing over periods. The buyer gets this, and the seller gets the expected discounted payment, and there is some discount factor, which is common in this specification. So how does the game work? At the beginning of every period, the seller offers a mechanism. The buyer accepts or rejects. If the buyer rejects, we have no trade and no transfers. If the buyer, and we move on to the second period or the subsequent period. If the buyer participates, there is an allocation determined. And if the allocation is trade, the game ends. So in that sense, the problem is very simple, because only if there is no trade, we move on to the subsequent period. So limited commitment here binds only if no trade realizes. So under full commitment, we have the standard revelation principle. So when we have the standard revelation principle, the optimum is to repeat the static mechanism every period. So the static optimum in every period is a direct mechanism. So now a direct mechanism is just a mapping from types to distributions over allocations. So in this model, the allocations are these Q's and X's, but nobody writes mechanisms like this, right? What we write when we have transfers, we say, look, instead of randomizing over the allocations, because we have because payoffs are linear in types and transfers, we are going to write down the phi instead as a probability of trade and an expected transfer. So eventually, this formulation here becomes a probability of trade. So a rule that specifies for each theta a probability of trade, and a rule that specifies for each theta an expected transfer. That's how we operationalize the revelation principle in everyday life. You never see these 5 things written. You only see the Q and the X. What is embedded here is that the lottery over those things has been already run, and we have already used the fact that everything is linear to get to this simplification. Sometimes people use a simplification when it's not actually justified. By the way, that's okay. So the buyer reports the truth and participates. And what's the optimum here? Well, if there is a belief, which we call mu1 bar, which is theta L over theta H, that's the belief that below that, if your prior is below that threshold, the optimum is to sell at a low price and sell to both. So if the prior is low, below that ratio, it's better to sell at a low price and sell with probability 1. If the prior, on the other hand, is high, it's above that threshold, then it's better to sell only with probability mu times theta h. Why? Because at mu1, you see that these 2 times this is theta l, so you're just indifferent. So at mu1, you're indifferent between selling to everyone at theta l or selling to theta h only with probability theta l over theta h. At prior above mu1, mu times theta h is higher than theta l. So the commitment optimum is to charge the low price if mu1 is less than this threshold. So Q of theta L, Q of theta H equal 1, and X of theta L, X of theta H equal theta L. And if the prior is high, so you're optimistic that you're facing a high value buyer, the optimum is to charge the high price and then solve with probability 1 only to the high type. So the low type does not get the good and does not pay anything. And then either the game, so if we have a low prior, the game will end for sure in period 1, because we're going to sell the good and we're going to go home and we're going to be happy no matter if there is commitment or there is no commitment. The problem with non-commitment arises if the mu is high, because then we're going to ask a high price, and if the buyer does not accept, then the seller is stuck with the good. So either the game ends in period 1, so no issue, or trade never occurs under commitment, because under commitment, you commit to charge theta H, theta H, theta H. The commitment is to repeat the static optimum forever. And that is, of course, hard to swallow. No seller or no government will just say, okay, I'm never going to sell this asset forever because nobody got it. So the optimal mechanism is not sequentially rational. And that's basically what got me started with my thesis. With positive probability, the seller is stuck with a good at tier 2 and is tempted to re-optimize. We're going to stop here and then we're going to continue after lunch.